Okay, so modular arithmetic is one of these things that once you truly understand it and assimilate the thought process behind it, it feels a little bit like unlocking a part of your brain since it gives a way to solve very seemingly hard questions in a very short amount of time and with very little computations. Even though if you think about it, the idea isn't really that deep. If you've never seen this before, then this is definitely something that, at least the first time I saw it, I thought was quite surprising, and it is incredibly powerful. The first theorems, I mean, we've seen a few theorems that might no longer be considered trivial, like Bezout's identity. I don't think that's like an obvious thing. But the first major theorems we will see will all be phrased in terms of modular arithmetic. So let's get started and let me tell you what I have in mind with this topic. So the first thing I want to ask you, which is one way to motivate this topic, is the following idea. So right now, ignoring, remove this, the AM versus PM thing, it is, and also let's ignore the minutes as well. So right now, ignoring AM and the minutes, what time is it, right? So, and the minutes. Right now, it is 11 o'clock, right? 11 o'clock. One question that I have for you is what time, if you're wearing a watch, like an analog clock, what time will it be in 2 hours? If it is 11 o'clock right now, in 1 hour it will be noon, so 12 o'clock, and an hour after that it will be 1 o'clock, right? So 1 is the answer. What if I wait 12 hours instead of 2? Well, in 12 hours, the small dial on the watch will have turned a full circle and it will indicate the same time it is now. Of course, like I said, I'm ignoring AM versus PM for now, since I don't think that's not really important for this example. So what time will it be in 100 hours? And what I want you to understand about this question is that you do not need to count 100 hours individually to answer this, right? That's the trick. Okay, so some people are writing in the chat, it will be 3 o'clock. Now, I don't know if this is true or not, but I can figure this out. So the key insight is that every time 12 hours go by, the time doesn't change in that the dial will indicate the same time on the watch, right? So the trick is, of course, I take 100 and I divide it by 12, and that should be, what? Let me think about this. 100. Okay, maybe I should have prepared this. How do you divide 100 into 12? Can anyone tell me what's the quotient? What's the remainder? Okay, thank you. Times 8 plus 4. Okay, that makes sense. And okay, everything that's been said in the chat is consistent then. So if I divide 100 into 12 and I wait 100 hours, that's the same, because of this equal sign, that's the same as waiting 12 hours 8 times and then an additional 4 hours, right? So this is, in terms of the watch, in terms of the clock, this is actually the same as waiting 4 hours. Because every time I wait 12, it's as if I hadn't waited anything at all, right? The 12 doesn't matter. So what we're going to formalize in a little bit is the idea that mod 12, meaning on the clock, 104 is the same thing. So to answer the question, If it is 11 o'clock right now and I add 100 hours to it, well, that kind of should be the same as if it were 11 o'clock and I just waited 4 hours according to the clock, right? And if I simplify this, this will be 15, which on the clock is of course the same as 3. So the final answer is indeed 3. And this is how you can figure it out by dividing and finding the remainder. Notice that the number 8 plays no role at all in any of these calculations. If I had made a mistake and written a 9, everything would still be correct. So the insight is the quotient doesn't matter for the type of questions that I want to answer. So hopefully this example is clear. Let me formalize this idea a little bit. Before I do that, maybe let's make a diagram. Maybe this. So this is the clock. And the key insight is top will be 12 o'clock or 0 if you think about waiting no time at all. Let me see if I can more or less get this to match. So 1, 2, 3, 4. I'm not only writing the time that these points represent, but how long I am waiting, right? So 7, 8, 9, 10. I mean, you're all familiar with this. After 11 hours, 12 hours, then 13, 14. And of course, I can do this for the negative numbers as well, right? If I wrap around the other side, I could think of 11 as -1, -2, -3. In terms of waiting hours, this would be like, I don't know, like turning back time or something like that, right? You can obviously can make sense of this. And this goes on forever. So for example, if I were to continue doing this, wrapping the numbers around the circle for forever, the next number here would be 16, and then 28, and so on, and also all the negative numbers, right? So in other words, what am I doing by a clock? A clock is a partition of the integers. I recall that this set is a ring. Now, I didn't explicitly define a ring. I've mentioned it several times, but in case you were wondering, it's a semi-ring, which I did define, with inverses, with additive inverses. Commutative, you should add this. It's a commutative semi-ring with additive inverses. Now, if you think about the clock, every property I defined that can be called a ring, that is a commutative semi-ring with additive inverses, is still satisfied on the clock. I can still add and multiply, and many of the rules that are true for the integers are true on the clock, right? If you multiply something times 0, well, you get 0, right? If you wait 0 hours, nothing changes. If you multiply times 1, nothing changes. But the first thing that I want to show you is that the clock behaves like a ring, or let's say is a ring as well as a ring too, but it is different. It is different in some senses. So this is another example of a ring, but of course it isn't the same structure. For one, the clock is finite. The clock only has 12 elements, and the integers are infinite. But here's another important difference that I want to highlight that will make more sense as we study this with in more depth, right? So here's another key insight. If it is 2 o'clock and you multiply it times 3, is that the example I want? No, that is not the example I want. If it is 3 o'clock and you multiply it times 4, and I haven't defined what it means to multiply time, but of course you can understand this as waiting 4 hours 3 times, right? This is just by definition, let's say. So if you do this, what time will it be? Assuming you start, say, at noon or any time, this is the same as 12. But on the clock, we just said that 12 and 0 are the same thing, because waiting for 12 hours is the same thing as waiting for 0 hours. So these two numbers, these two times, represent the same object, the same number. But this is kind of weird, because 3 and 4 are not 0 even on the clock. So 3 is not 0. These are different times. And 4 is also definitely not 0 on the clock. And yet I managed to multiply two non-zero things and got 0. This is something that is impossible in the integers. If you multiply two integers and you get 0, well, one of them has to be 0, right? There's no other way. So this is a key difference that right now I will not give it a name, but this is just to highlight the fact that even though both of these are rings, there's associative properties, commutative properties, distributive properties, all of that, these structures are very different. And we need to keep that in mind because that will be more important as we study this. Definition. Let me formalize these ideas. Let M be something at least 1. 0 will not make sense in this case. And AB can be any two integers, negative, positive. We say A is congruent or equivalent, congruent to B mod or modulo M. In symbols, I will always use the symbol A sub MB, or sometimes in some textbooks you might see it like this, and then in parentheses written mod M, right? Sometimes they don't use this symbol either and just the equal sign. That is okay too, but I want to emphasize that these are different things. Symbols. And when does this happen? Well, it happens when A and B have the same remainder when divided by M. They represent the same time on the clock with M hours. And a very succinct way of writing this is that M divides the difference between them. Because if M divides the difference between them, then A is the same as B plus some multiple of M, right? Now, that thing that I just mentioned is part of the problem set for you to prove. There are I think 4 or 5 equivalent ways of understanding this. The one I just gave you is the definition, so there's nothing to prove here, right? This fact implying this fact is by definition. That's how I'm defining the symbol. So in the proof of the problem set, I think this is 1 implies 2, and then you can just say this is trivial because that's literally how it is defined, right? That's how this symbol makes sense. But the other equivalences might take a little extra time, like it isn't immediately obvious that this happens, and by this I mean this property right here, if and only if A and B leave the same remainder when divided by M. Okay, so let's see some examples. Oh, and some notation that will be convenient. Actually, before I mention this, so here's a fact. More than a fact, I think I should leave this as an exercise. This is something worth proving. This symbol is an equivalence relation, and thus it partitions the integers. Equivalence relation on the integers. This is very straightforward to prove. This is why it's an exercise, and it's not really a problem in the problem set. If you're struggling with transitivity, you may need to move things around, but there's really nothing tricky going on here, right? So something that I defined previously, and if you don't remember, I suggest you go back to my previous notes. Whenever you have an equivalence relation, you can define the equivalence class, right? And this is the set of all things that are related to A under the equivalence class, sorry, the equivalence relation, which in this case is congruence. Now, this is a bit cumbersome to write down, and I will only talk about one equivalence relation for the remainder of this chapter. So the notation that I'm going to use is I'm just going to write a subscript M, and I'm going to drop the 3 parallel lines, right? This leaves no ambiguity because I haven't defined the square brackets in a subscript of a number in any other context, so I think this should be clear. Let's look at some examples to formalize this so that it makes sense. The first example I should mention is perhaps the easiest one, which is what happens mod 2? So let's say 0. I can write any integer there. What is this mod 2? Well, by definition, this is the set of all integers, I don't know, k, integers, such that 0 is congruent to k mod 2. That's the definition that I gave of the symbol of square brackets, right? There's nothing else going on here. But if we want to write this in a little more detail, well, this is the integers. I'm not going to repeat that notation since we already know that that's what it means. By definition, congruence means that 2 or m divides the difference. And the difference is k minus 0, which lucky for us is just k, right? And when does 2 divide k? Well, that happens precisely when something times 2 is equal to k. Maybe I can write one more step here. So there exists, I don't know, s integer, of course, such that 2 times s is k. But if you want to write this in an even more succinct fashion, I can just substitute k for 2s, and there's no need to refer to the second variable, right? This is just s. If you're struggling to see how these two are equivalent, then I suggest you try proving that these two are the same set. But this is mostly just notation, right? And this is what we are going to call an even number. This is what we're going to call the set of even numbers, right? Now, mod 2 is kind of boring because the next number, the next integer in consideration is, of course, 1. What is 1 mod 2? Well, it is all numbers such that so and so and so on. But if you simplify this, what you should get, maybe I should use the same variable, is all numbers that are of the form 2s plus 1 or minus 1, where s is any integer, right? And these are called the odd numbers. Odd numbers, right? And why, maybe I could be a bit more, okay, let's just do the next example. So what happens with the next integer? The next integer after 1 is, of course, 2. But let's just expand this out and see what we get. This is all the integers such that 2 divides what? 2 minus k, right? That's just the definition. But this is then the same as k such that there exists an s such that 2s is 2 minus k. But then this is the same as there exists an s. And there's something that you can do here, right? You can write this as minus 2. Actually, let me just change the order since we already know this is an equivalence relation. The order doesn't matter, right? So I can just, maybe this makes it a bit easier to write down, more readable. So this is plus 2 equals k. And then I can just substitute k. And then this is 2s plus 2, where s is any integer. But 2s plus 2 can be factored into 2 times s plus 1, right? And if s is any integer, well, in particular, I can just substitute in something like s minus 1, right? So the point that I'm trying to convince you of is that this is just the same as this. These two are the same set. And if you're getting confused by this, maybe I should use a different variable like t, right? If at any point you feel, I mean, I think this is fairly straightforward, but if there's confusion at any point, feel free to ask me or try proving these equalities yourself by double containment. You'll see it's very, very simple. And this is, of course, the same as 0 mod 2. So here we got something interesting. Just after 0 is different from 1 and 2 mod 2, this class is already the same as 0. So I already have a repetition. So this structure, this clock, a clock with just 2 hours, 0 and 1, isn't that interesting? Okay, I have a question in the chat. Why am I able to change 2 minus k to k minus 2? That's a good question. I will reply to this as a comment. So remark, it's an abbreviation of remark. M divides A minus B if and only if, maybe I should write it down, M divides B minus A. That is simply because if two numbers divide each other, then plus minus those two numbers also divide each other. Adding a minus sign on either side doesn't change whether two numbers divide each other or not, right? So this is just minus A minus B, is what I'm saying, right? So maybe if I want to be a bit more explicit with the property that I'm using, in general, A divides B if and only if plus or minus A divides plus or minus B, right? I can add or remove plus minus on any side of this vertical line, and they are all equivalent. And if you want to see how, then this is a very, very simple exercise. But if you don't see this as obvious, then I suggest you try writing it down, or I'm happy to fill in the details as well. So this is the property that I'm using, and this is the property you need to show that this is an equivalence relation. In particular, the symmetry depends on this fact, right? Maybe I can write that down as well. So in particular, M divides A minus B if and only if M divides B minus A. I can just change the order. On one side, this means that A is congruent to B, and on the other side, this means that B is congruent to A. So this is just symmetry, right? This is symmetry, what I'm using. This is how you would prove that it is a symmetric relation. Okay, so what does this structure look like? So the set of integers partitioned over this congruence, mod M, and I'm going to use notation again. Notation will be, this set will just be denoted by Z sub M to avoid all these lines. What is this set equal to? Well, this will be the set of 0 sub M, 1 sub M, all the equivalence classes. But as you can see with the example of the clock or the example of mod 2, there are only finitely many classes because after a while they repeat each other. They repeat, right? They repeat, not each other, they just repeat. And this happens exactly after M steps because M mod M is just 0, right? This happens because actually maybe I can be a little bit more explicit with this. So here's another example. Here's another example. So what about the clock, right? We already know that 0 o'clock waiting 0 hours is the same as waiting 12 o'clock. And why is that? This is the same as waiting 12 o'clock because 0 are just the multiples of 12. Similar to how I developed the example of mod 2. This will just be 0, 12, 24, 36, or whatever, and so on. The negatives are also there, naturally, right? What would be mod 12? Well, that's all the numbers that are congruent to 12 mod 12. So of the form 12 times something plus 12, according to the same thing I just wrote down up here, right? So this will be 12. Then 24, you always add 12 to get the next number, right? 36, and so on. And if you subtract 12, then you get 0 and minus 12 and so on. But if you look at this, it's the same set. It's just shifted, right? But these are the same set, right? So the answer is that how does the clock look like? Well, there's 0 o'clock, which is every multiple of 12 is contained here. Then there's every multiple of 12 plus 1. Basically, every way that you can get 1 o'clock. For example, 13. If you wait 13 hours, it's the same as waiting 1 hour, right? Then there's 2 o'clock, and then there's everything until 11 o'clock, and after 11 o'clock, they repeat, right? So in general, this is how you can find all the classes. Now this structure has a natural algebra to it, so the ring of congruences. The ring of congruences. So how do you multiply two objects like this? How do you make sense of this product? Well, the same way that when I was defining the integers, the most natural way is just find two representatives, A and B, multiply them, and find the class, right? And the same thing happens for the sum. So this is how you define, this is a definition. This is how you define the operations on these objects. So just add them together. This is the easiest way of doing that, right? Does this make sense? So here's an exercise. Show that these operations are well defined. Well defined, I mentioned what it means for something to be well defined in a previous lecture when I was constructing the integers. It basically means that the product and the sum don't depend on the representatives, right? Whether, for example, let's say that you're adding the class of 1 o'clock, so 1 mod 12. Someone else might be thinking of 13 o'clock instead of 1. Well, adding this shouldn't change that. You might get a different representative, but you should get the same class. So this is an exercise, and if you're struggling to understand these abstract definitions, I suggest you go through with it. It's a bit tedious in the sense that there's nothing tricky or insightful about it. It's just writing down the definition, chasing definitions, as they say. But it is fairly straightforward in my opinion. Now, in the next tutorial, you will see quite a sophisticated example of how you could solve a very difficult question using modular arithmetic. But let's work our way up to that in the in the lectures. Let me think about this. Basic properties. So this is basically saying that the modular class, so this object is always a ring with the product and the sum that I just described is a ring as defined earlier in this lecture, right? And you can assume that it is a ring. Of course, I suggest you do the exercises, but as far as the problem set in the final exam are concerned, you can always assume that this is a ring. Now, it is not much more than a ring generally, so be careful not to assume that you can do some weird stuff like finding the multiplicative inverses, for example. That's something that we have to look into. Okay, so one property would be proposition for every k natural number. If A is congruent to B mod M, and of course, if I'm using this symbol, you already should implicitly know that I mean that A and B are any integers and M is at least 1, right? If M is 0, then nothing makes sense and the definition doesn't apply. So this is part of the assumptions if I'm using this symbol. Okay, so this tells you that A to the K, which is A multiplied with itself K times, is congruent to B to the K, which is B multiplied with itself K times. Now this might seem simple enough, and if you want, we can prove this property, but an example of how you could use this. Let's say that you're trying to find the remainder of 497 when divided by 498. Sorry, let me make this a little bit more challenging, perhaps. What happens if you take this absurdly large number, 497 to the, I don't know, 500? Actually, 500 is kind of close. How about 1000? That number is a number too large for most household calculators to compute, right? And you can definitely not compute that by hand. But of course, the question is what kind of representation of that number would be useful? And let's say that we're trying to, for whatever reason, determine the remainder of this huge number when divided by 498. So one thing we can do is we can just substitute in the basis of this exponentiation by -1, because 497 is congruent to -1 mod 498. The exponent doesn't change. There is a way to reduce the exponent as well, but that will take a lot more theory that is not really part of the scope of this course. So right now, the exponent, we don't really have a smart or a clever way of reducing it. We might have some more elaborate techniques in the upcoming lecture, but not as of right now. So 1000 is an even number, so -1 to an even number is just 1. And notice that I reduced a really difficult problem on the left to a really easy computation on the right just by reducing mod an adequate number. Now, this example might be very simple, but I will share with you some more elaborate examples where this sort of reduction is not that easy to spot. And without this reduction, the problem becomes probably impossible to solve otherwise, especially if you think about this in a computational setting where you can just compute absurdly large numbers, and there's no other way to think about this other than reducing them in this context, right? So are there any questions with what I've explained so far? Do the definitions make sense and how you would apply them? I will give you a minute to think about if you have questions. By the way, in case you didn't see the in case you didn't see the announcement, on Piazza there's a special section for you to share your solutions to these exercises that I am writing down randomly throughout the lectures. And if you give each other feedback, that could be really useful for all of you. So I strongly encourage you to do that. Please don't share solutions to the actual problem sets, since that is part of the evaluation. But like I've mentioned before, these exercises that are simpler than the problem sets are also good candidates for for me to just copy paste into the final exam. So make sure that you try to solve at least some of them. It's part of the process of learning and understanding all these things. I know it might be a lot of material sometimes, but feel free to stop me and ask questions if something's unclear. Okay, so let's do maybe one more example, and I will show you something interesting. Let's compute the multiplication table of the congruence classes mod, I don't know what's good, let's say mod 5. There's something interesting about 5 that is different from the clock, right? The clock, which has 12, is not a prime number, it's a composite number, but 5 is prime. And let's see what we get. So this is the class of 0 mod 5. Now, I'm just going to write down the representatives because this will be very cumbersome to write down, and this is how most textbooks do it as well. So just keep in mind that when we talk about modular arithmetic, you're always thinking about the modular classes. This is the product, by the way. But you only write down the representatives, and that is good enough. Okay, so this is a multiplication table. 0 times 0 is 0, and it doesn't require too much imagination to see that anything times 0 is 0, therefore this row is all 0. Now, I'm only going to worry about the upper right triangle, everything above the diagonal, because the product is commutative. So this table must be symmetric with respect to the diagonal because of symmetry, right? Because of commutativity. Okay, so 1 times anything is just itself. So 1 times 0, I'm going to ignore that because it's already written down on the table. 1 times 1 is 1, times 2, this is just, 1 is the identity, right? So this is just copying down that row. Now it gets a bit more interesting. 2 times 2 is 4. 2 times 3 is 6. But 6 reduced mod 5 is just 1. And then 2 times 4 is 8, which is just 3 mod 5. And then I think this is 3 times 3 is 9, which is 4 mod 5. This is 2, and this is 1 again, right? And that's all I have to do. Let me see if I'm missing anything. So the diagonal consists of all the square numbers, right? This is 1 times 1, 2 times 2, 3 times 3, 4 times 4. Now, there's something interesting here. 1 times 1 is always 1, regardless of who m is, what the modular class is. If I'm reducing mod a huge number, 1 times 1 is always 1. This number right here, the last corner, the lower right corner is also always 1. Who can tell me why? So these are always 1. Or any m. So the first one is clear, that's just 1 times 1. But why is 4 times 4 1? And why is 117 times 117 also 1 mod 118, right? Why is the lower right corner of this table always 1? Who can tell me why? Yes, exactly. So someone in the chat answered this, Brendan, I think. Right. So the number is always the last one, right? So m minus 1 times m minus 1, or let's just write it as m minus 1 squared, which is congruent to minus 1 squared, which is equal to 1. So this is always true. These are not interesting, right? The ones that are interesting are the number ones that appear outside of these two examples. And isn't that weird? How can, like, what does this number 1 mean over here? This means something different, right? This number 1 is what you get from multiplying 3 together, right? So 2 times 3 is congruent to 1 mod 5. But if you think about this, if these numbers were rational or real numbers, if you have something of the form x times y equals 1, then this usually means that x is like the inverse of y, right? Or that this is like 1 over x, something like that. You can divide x on both sides. So this situation is special, and I will explain why in a second. If 2 times something is equal to 1, that means that 2 times, let's say, 3 times t must be congruent to t. But t can be anything, right? In other words, if I am able to multiply 2 or any fixed number, for this example, let's say 2 times something and get 1, that means that I can actually get every number by multiplying 2, right? 2 times something is every possible number because it's just t. This does not happen in other numbers, and you can easily see why this is a special scenario. So let me scroll up to the clock, because the clock, like I said, is different. So primes and non-primed and composite numbers behave differently. For example, the number 6. Let's think about the multiples of the number 6 on the clock. If it's noon or whatever, and you wait for 6 hours, then it will be 6 o'clock. If you wait for 6 hours again, it will be noon, and so on. I mean, not noon, midnight, I guess, but like I said, AM, PM doesn't matter. So waiting in intervals of 6 hours can only yield two possible numbers, 0 or 6. The multiples of 6 are just 0 and 6. The multiples of 3 are just 0, 3, 6, 9, and so on. 0, 3, 6, 9, and goes around the clock, the quarters of the circle. So it is not always the case that the multiples of a fixed number will give every possible number. Now, of course, it is always true for the number 1, because the number 1, the multiples of 1 are just, 1, 2, 3, 4, 5. You get every possible number. Can you find a different number on the clock whose multiples will produce every other integer. So let me scroll down and write down that as a question. Because here it seems like every row contains every number. So maybe I should write all these down. So let me just write down oh, that's horrible, the reflection, right? So this is 0. This is just 0, 0, 0, 2, 3, 4. This is just 3. And this should be 2 and 3, if I'm not mistaken. If you see a mistake, please let me know. There's something weird about this. So yeah, this should be 1, right? Yeah, thank you, thank you. Someone, yeah, perfect. So notice that there's something interesting here. Every single row contains every single number, but shuffled, right? I mean, of course, except the row 0 and the column 0, because those are always 0. But every other row contains all the numbers. The row of 1 obviously contains 0, 1, 2, 3, 4. The row of 2 contains 0, 2, 4, 1, 3. That's all the numbers mod 5, but in a different order. The row of 3, in other words, the multiples of 3 are 0, 3, 1, 4, 2. So again, all the numbers, but in different order. So this is weird because this doesn't happen on the clock. On the clock, the multiples of 6 are just 0, 6, 0, 6, 0, 6, and so on, right? You don't get every possible number. But it seems like if you could get every possible number, in particular, you could get 1. And if you can get 1, then this argument should convince you that you should get every possible number. Maybe I can make that more precise as an exercise. So this observation is made precise in the following sense. So let's say that fix m and a an integer. So if there is, maybe I can write this a bit better. So there exists b integer such that a times b is 1 mod m if and only if for every integer t there exists a b sub t, maybe it could depend on t, right, depending on our choice, such that a times b sub t is t. So what I'm saying by this is think about the multiples of a number. That is, think about the row of a multiplication table. If that row contains the number 1, then it must contain everything with no repetitions, right? Because it's just a finite set. So if you're shuffling all the numbers, then you get no repetitions because all numbers must appear. And conversely, if all numbers must appear, well, in particular, the number 1 appears. So isn't that interesting? So here's a question. Mod 12, the multiples of 6 are 0, 6, 0, 6, and so on, right? They just alternate. You don't get a number 1 ever. And actually, there's a bunch of other numbers that also don't appear. The number 3 doesn't appear on this list. So mod 12, this isn't true, that every row contains every number shuffled. It is not true. So here's my question to you, and maybe you can think about this. What other numbers, obviously 1 has this property, but what other number have the property that their multiples mod 12 produce every number, or in particular the number 1, because this exercise tells you that if you can produce the number 1, then you can produce any number, right? If a row contains 1, it contains everything shuffled with no repetitions, and that's an if and only if. Okay, so Okay, maybe not what numbers. I just want you to give me another number. What other number? And by other, I mean other than 1, because of course 1 times 1 is 1, so the multiples of 1 give everything, right? That's always true. The row of the number 1 is always the numbers in order. You don't even have to shuffle them. So does the question make sense? Who can tell me what other number? In other words, if it's noon and you're going to wait for a fixed interval of time, but you can only wait, let's say, 6 hours at a time, then that will not produce every possible hour. It will only produce 0, 6, 0, 6, 0, 6. What interval of time other than 1 can you wait and guarantee that you will eventually reach every number on the clock? Who can tell me what that is? Okay, so someone is asking if m minus 1 produces every number. Okay, that's interesting. So m minus 1 produces the same numbers but in reverse order. So yes, m minus 1 has this property. That's a good observation. Okay, so I think we have the full answer. I think Johnny answered in the chat. 5 and 7. Indeed, if you look at the clock, let's see if this is true. So according to Johnny, if we wait in intervals of 5 hours at a time, we should be able to get every hour. According to the exercise that I wrote down, it is enough to find the number 1 on this list, and then we should be able to produce every other number by just multiplying times t, right? Okay, so if it's 0 o'clock and you wait for 5 hours, it's 5 o'clock. If you wait for 5 more hours, it's 10 o'clock. If you wait for 5 more hours, it's 15 o'clock, which is 3. 5 more hours, it becomes 8 o'clock. Uh, 8 o'clock. 5 more hours, it becomes 13. Hopefully I'm making this correct. And 13 is 1. So indeed, the multiples of 5 contain the number 1. The row of 5 contains the number 1. Therefore, it must contain every number. So 5 has this property, and I leave to you to figure out that 7 also has this property. And I think no other number has this property. So what is special about 7 and 5 mod 12 that, for example, 6 doesn't do? We will answer this question in the next lecture, and thinking about this will eventually yield something known as the Chinese remainder theorem. That's a bit more sophisticated than what I'm saying right now, but it's the same line of reasoning. If you attend the tutorials, then you will see an application of this to a really difficult or like a challenging exercise. Okay, so let me stop the recording just for the sake of time. If you have any question, then please let me know if something's unclear. I will hold my office hours now, so you're welcome to stay. And yes, 11 is also has that property because 11 is m minus 1. So 12 minus 1 is 11. So yes, that is true. You get the numbers in reverse order. Okay, so if you have no questions, then I will see you all on Thursday to continue with the lecture, but feel free to stick around and for the office hour.